Our speaker today is Dragana Laketic. She has a master in electrical engineering with a thesis on artificial neural networks for time series prediction. Her PhD in computer science had the topic of emergence and dynamical hierarchies in biologically inspired computer hardware. As a postdoc, she worked on conductivity of carbon nanotubes and its variations as the effect of the applied magnetic field. Currently, she works on the dynamics of quantum entities. Today's talk gives an overview of her work. So without further ado, Dragana, please take it from here.
Emergent computations for emerging technologies, title of my today's talk, and also the title of the research plan, as mentioned. And it describes in a way what I plan to do in the coming years regarding research. And to provide a context and give a better understanding of the planned research activities, I will first say a bit about previous research activities. And I will only give a brief overview just to point most important things from each of them. And for the planned research activities, I will speak about in a bit abstract way. And I'm doing that on purpose, because I would like to show that there is room for different specific ways how to conduct some of these research directions. So I would like to start with the PhD thesis, where I looked into complex systems evolved in nature. And in particular, we see these examples of complex functionalities that are performed by natural systems. And on the right-hand side of the slide, there is a schematic view of how these systems are organized. I borrowed and adapted this schematic view from the work of some contemporary philosophers, actually, but it is very nice description over the main principles. First of all, the systems which are evolved in nature are built in a bottom-up fashion. So at a very low level, there are some entities that are undergoing certain dynamics, and then we can observe entities at a higher level, which then impose certain constraints over the lower level entities, and which also discard some too much information that is important for lower level entities. They bring in some novelty at a higher level, and in that this so-called triadic system functions. On the left-hand side, it is just a brief summary of the PhD thesis, where inspiration was taken from a minimal living system, the Camerton model, and derived conceptual framework for such a system, which could be adaptive to environmental fluctuations. And I suggested implementation in analog electronics. So this would be just one cell adaptive to environmental fluctuations. But as said, any complex functionality should be built in a bottom-up fashion and organized in a dynamical, hierarchical way. Then dynamical hierarchies followed me further in my research, which was in unconventional computing paradigm known as computations in materia, and the work within NASA's project. And there I looked into one particular material, which was carbon nanotubes dispersed over polymer molecules. And on the left-hand side, we can see 3 micrographs on the top, which represent this, show this material for 3 different concentrations of carbon nanotubes. The image below is the material spread over a golden microelectrode array, which was a board which would be plugged into this green board, the Kovo board, which was developed by my colleague, Rune Laketic, who was a PhD student of Gunnar Tufte at the time, also my supervisor for a PhD thesis. And this board would be used as a mediator between analog domain of the dynamics that was going on in a material substrate and a digital computer. And digital computer was the place where genetic algorithms were run in order to configure the material, to read response, and to guide the configuration of the material towards the desired functionality or towards the desired solution of the computational task. The schematic view is of the whole system is shown as well, and for such a setup for the computations in material, we have recognized 3 hierarchical levels, primarily level of physics of the material, then level of measurements, where these ADDA conversions are happening, and finally the level of interpretations, because we need some intelligible answer to the task that we impose to the system. And we had a lot of interesting discussions where actually computations happened, but for me it was very interesting to see how we could describe this hierarchical system. So I looked into one particular work from artificial life community, which is based on information theory. And it starts with the description of the system from different levels, defines conditional entropies for such descriptions, and then looks into relations between different conditional entropies. And based on these relations, we can conclude whether higher level description contains some novelty, whether there is some loss of information from the lower level, and basically we can put the system into hierarchical view on computations. So with that, I have also, for this particular system with carbon nanotubes and the physics that happens at this very low level, I have tried to describe the system in this fashion, and the publication that came out of it is also shown in the slide for more information. And the conductivity of carbon nanotubes captured my interest, so I came across this interesting property, and that is that it can be changed with a magnetic field. So not only the value of the conductance of carbon nanotube can be changed, but also the character. So if we have a metallic carbon nanotube, which is exposed to magnetic field parallel to the axis of the nanotube, we can see the change from metallic to semiconducting and vice versa, which is a manifestation of so-called Aharonov-Bohm effect magnetic field has on phase of the electron when in a quantum regime. So I found it interesting and suggested like a toy model, made a toy model of a computing cell, which would be based on a MOSFET transistor whose channel is realized by a carbon nanotube, and which would also possess some magnetic field control, which would make this channel conducting or semiconducting, and based on that, transistor would be closed or opened and generate 0 or 1, some binary response. This was the simplest case that was considered. And for such assumed computing cells, we could make them into certain arrangements for achieving computations. The example shown on the third figure from the left is one-dimensional cellular automata. And if we imagine that each cell, like the one just described, contains a carbon nanotube-based MOSFET transistor and is stirred by magnetic field according to some rule, cellular automata rule, we can see patterns emerging over the time if we run the simulation. So on the rightist figure shows example of 16-cell one-dimensional cellular automata, which is developed in time. And according to the rule 110, cellular automata rule 110, which was proven to be Turing complete for computations. So that would be just a suggestion for how we can do actually computing with magnetic field in carbon nanotubes. And this quantum world, quantum domain also...
Can I ask a question about this?
Sorry?
Can I ask a question?
Yes.
So what's the advantage of using magnetic fields? Because in reality, it's actually really hard to control those quickly and very
yes.
precisely in space.
Yes, I would agree, because this was, as I say, like it's a toy model. It was a property that captured really my interest, as I don't come from physics. So this was like a toy model, but I'm looking more into collective computations. So as in this material I just talked about, we have carbon nanotubes dispersed over a certain area. So if we expose it to an environment which is magnetic, we could see different conductivity if we change direction or intensity of the magnetic field as a whole. So we could see some emergent patterns. That was more the vision and the vision I had. But in this simple example, it was more like to run this Schrödinger-Poisson solver and to see how it would develop over time and similar. So yeah, so we could, it was more towards the collective computational properties that I was aiming at. So yes, can I go further?
Yes.
You can try. Yes.
So yeah, I come to the quantum world, and it was more learning about quantum processes, quantum entities, and I came into a very interesting example of spin dynamics, and it is a mechanism that is one of the suggested mechanisms to be responsible for avian magnetoreception, or one of the mechanisms which possibly enables birds to navigate in Earth's magnetic field. It is based on spin dynamics performed by a radical pair, which is generated by light hitting certain protein molecules. And until it decoheres, it undergoes certain dynamics, and the resulting classical products of such dynamics upon decoherence carry information about the magnetic field in which the whole process took place. And I will not go into details. It is very interesting, but I threw out the equations which describe this process. And for me, it was interesting to put it into a hierarchical view. So I tried to, again, use this information theoretic approach and put these processes into this framework. And in that way, I basically showed that the signal which carries information about the Earth's magnetic field and helps birds find a way is the emergent result of the coherent spin dynamics which take place in the bird's eye. And with that, I come to the challenges I would like to try to address in my research, future research, and the motivation comes from the challenges that semiconductor industry, on which basically all computing devices we are using in every day, and not to mention our computers, are based, and that is because of miniaturization and scaling down. So there are many low-level effects that are coming into play, and there are many clever design techniques that are being used to mitigate them. Some examples for transistors are FinFET transistors or all-around gate transistors and similar. But there are also emerging technologies which we are witnessing that try to make use of these low-level effects and not only mitigate existing effects in existing semiconductor technologies, but also to build new technologies based on these effects. So my goal would be to design a novel computing device, which is based on the manipulation of the dynamics of nanoscale or quantum entities. And with that, to say a novel would be maybe a too strong word, because I would also like to improve the existing designs. And to start from the beginning is what is computing? Computing is basically information processing. We have some information processing system which takes input information on one side, processes it, and provides output information on the other side, which is the result of our computational task. But since information is physical, we are actually speaking about physical device, which on one side takes a physical carrier of the information, processes it, and generates physical carrier of the output information. And of course, this physical device has different parts, and we have to have some physical substrates which is dynamical and which can be manipulated in a certain way. And I will refer to this substrate as a computing substrate. Then we have to have a certain part which enables us to manipulate it and to impose certain constraints so that we guide the dynamics towards the desired result. And finally, we need to have interpretation level part which enables us to get understandable and intelligible response or result of the computation. And now how to do it, I will go through the things I have in a way already presented through my previous work, and that is to start with inspiration from complex systems which are involved in nature, and start looking into organizations of dynamical hierarchies, start looking into how to organize and manipulate low-level entities in a bottom-up fashion. And starting from the bottom, there is some computing substrate. And this substrate is assumed to contain some nanoscale or quantum entities, and for us to be possible to manipulate it. Also, it needs to host some interesting dynamics which can be further exploited towards useful functionality or computation. And to find this substrate, I would like to consult fields of physics, materials science, nano-electronics, and today we can do everything in computer simulations as well. And we are witnessing the time when we can do simulations and then search for building materials with desired properties. So that is also one way to go. But I would really like to consult some the findings from other fields. And in the example that I have given on the left-hand side as a sketch, there are some entities depicted as small sticks that are dispersed in a plane. And if we assume that under certain constraints and manipulation, they perform certain dynamics, they may form these closed 2D arrangements. And if we assume that these closed 2D arrangements have some novel property, which can be observed or measurable property, then we can say that we have some emergent patterns in time or in space, which can be observed as properties or some novel behaviors. And with that, I'm thinking like something they can start conducting current, or they can show some magnetic moment, or they can start blinking, just start emitting light or something similar. So we could start speaking about the higher hierarchical level that is emerging from the dynamics of the lower level entities. And of course, here I would like to put everything into a proper theoretical framework and to consult information theory in a wider sense, mathematics, because everything we do in research, if we don't have a firm theoretical description, it does not really hold, at least for me. And so if we speak further about achieving some useful functionality or getting result of a computational task, we would need to find a way how to manipulate, how to relate these emergents to each other and achieve the final goal, which would be the functionality or computation results. So to be interpretation also of these results. So to summarize the expected outcome of the coming years of research, it will be some novel unconventional computing paradigm. And again, I would like to say that it is not necessarily novel. It can be improvement of the existing ones, or even working within the challenges for the existing widespread technology would be interesting. What is always present is the simulation of the dynamics of these low-level entities, which I really find interesting and fascinating, especially in today's, over the last years, we see this many discoveries of some really nice properties of nanostructures. When put under certain conditions, they can exhibit very, very interesting dynamics. And so, yes, some simulation would follow the whole research, and to have everything described in a firm theoretical framework, I would like to consult information theory, because information is universal. It can be really recognized in many carriers, many substrates, physical substrates. And it is, I think, way to go towards universal description of computing systems based on dynamical hierarchies. And of course, if everything results in some useful ideas that can be implemented in physics in the lab, at least, I would like to see a proof of concept implementation of such a computing device. And throughout the whole steps, as I showed, I would like to consult other disciplines and, if possible, give also advanced interdisciplinary research, because today I think we can't really achieve anything if we just stay closed in our disciplines and one particular field. And now I would like to thank you for the attention. And of course, if there are questions I can answer, or either now or later. I don't know how much time is left, so yes, thank you.
First of all, thank you very much for the nice presentation. Are there any questions?
Yeah, so I have a question, because this sounds similar to something I've been looking into, and I was wondering how you would like to quantify how well such a system works regarding to a specific task.
Well, we can see, it depends what the task is. So I can take examples from computations in material that we did within a nascent project, where computational tasks were, let us say, like making distinguishing between two different frequencies, or making some pattern recognition, or there was a number of computational tasks that was examined. So we can, if going in with a such setup, we can say, like, measure the response and what we want to achieve, and then we can quantify. We can say this is the answer or not. And we can also make, like, if we give it as how can I say, example, if we give, it doesn't necessarily have to be computation, it can be any functionality because the two can be related. It's just different names we use. So we can also say like we want to achieve some functionality or, and then we can see if it really performs as we would like it to see performing, if it has the properties. So I would put it all dependent on the particular task that we give to the system.
Still, I don't fully understand. How do you model or map the observations of the system to a specific task?
So depends which kind of signals we take. We can take just electrical signals, or we can take then further interpreted to be read by a computer, for example, or we can like a simple 0 or 1, like that is the basic thing. So we can have some analog electrical signal and then translate it into a digital world, so we can depict it as a 0 or 1. Or we can have any other response dependent on which functionality we want to achieve. So
okay, thanks.
It depends
Okay, thank you.
Yeah.
Sorry for interrupting you. Are there more questions? Please speak out loud and.
Yeah. So may I ask? So yeah. So yeah, very interesting. Very interesting ideas. I was looking at so one of the slides in your this toy model. It almost looked like there was a kind of a fractal pattern emerging at this functionality level, if I understand correctly.
I haven't heard the question about
so it almost looked to me in one of the slides you showed where maybe you had this early toy model with the rod influenced by the magnetic field and then creating a certain patterns emerged, and it almost looked like a fractal where you show this. So is it possible to actually describe it formally as a fractal, or it just was modeled very much in the spirit of a fractal?
Yes, so that model is cellular automata rule 110. So dependent on different rules that are applied to how cellular automata evolves in time, we can recognize different patterns. And there is a whole range of patterns that can be explained at different scales of chaotic systems exhibited there. So this particular patterns that emerge can also be seen in the nature. It is a very well-known picture of the shell with the seashell with these patterns. So I can pass some references where all the possible patterns are analyzed, and also how system can go from one end of chaotic being ordered, then towards chaotic. There are 4 different categories that can be seen, and everything is analyzed. So I can pass the reference to this work, an area of work.
Okay, thank you. Thank you.
Okay, thank you very much. I think in the interest of time, thank you one more time very much for the interesting presentation.
Thank you.